Hello everyone, a very good evening to all. Myself Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So I welcome you all once again for this 10th interaction session on the NPTEL Course Experimental Physics 1, which is being flowed this July 2025 session with course code NOC 25 PH 51. So today we will be solving a few problems that will be covering the week 10 course contents or the lectures of the course. So if we so first we will discuss briefly the concept that was covered in this week's lectures, and then we will start solving the sample problems. So if you talk about this week's contents, so experiment related to platinum resistance thermometer are discussed. Platinum resistance thermometer were discussed. Then voltage and current characteristics of LR circuit. Then voltage and current characteristics of series LCR circuit was also discussed. And then theory regarding sensitivity of plastic galvanometer were discussed. Then the experiment related to the plastic galvanometer was performed. So let's first discuss briefly about series LR circuit and LCR circuit. Then we will start solving problems. So let's first discuss series LR. So basically a typical series LR circuit looks like, suppose this is R and this is L, and both are connected in series to a AC power supply, or we can write it. Suppose this is Vs, that is the supply voltage, then this is R and this is L, that is the inductance of the oil. Then the voltage drop across resistance will be VR, and voltage drop across inductance will be VL. And due to the voltage applied, the current flowing, suppose it will be time dependent. So IT is equals to Im sin omega t. Then if we uh, want to uh, calculate we want to determine the values of the voltage that is dropping across the uh, components. So this is series RL circuit. So total impedance will be R square plus XL square root over, where XL is omega L, and the phase tan phi will be XL by R. And if we discuss about the voltage drop across resistance, VR will be I into R. So both voltage and current are in phase, or they don't have any phase difference. And for inductor, it is I XL, which is I omega L, where current lags by 90 degree. So that's why that is the phase difference can be calculated. And if you talk about the power, so power is given by P is equals to VI cos phi, and cos phi is equals to R by Z, which is called as the power factor. So basically, if you talk about the components, inductor does not consume real power. It may store and release energy because, but so only the resistance dissipates power as heat. So we can say the applied EMF E square is VR square plus VL square. From this we can, this is the applied EMF. So now let's solve a few problems. Then we will, so as we proceed in the session, we will discuss more concepts if the question comes related to that concepts. So this is question number one. Question number one says the potential difference V and the current I flowing through an instrument in an ST circuit of frequency f are given by V equals to 4 cos omega t and I equals to 5 sin omega t ampere, the power dissipated in the circuit. So here the current and voltage expression is given. Voltage is 4 cos omega t, current is 5 sin omega t. So and we need to calculate the power dissipated. The options are option A 20 watt, option B 10 watt, option C 5 watt, and option D 0 watt. So these are the four options. I will give you a few minutes to try to solve this question, and then we will discuss what will be the correct answer. So let's solve this one. So the uh, so here power means, or here you see the voltage is given 4 cos omega t and current is given 5 sin omega t. So here we will calculate the average power over a cycle. So the average power P will be 1 by T 0 to T V I into dt. So if we calculate, it will be 1 by T 0 to T 4 sin omega t into 5 cos omega t into dt. That implies 10 by T 0 to T 2 sin omega t into cos omega t dt. So here 4 into 5 20. So 10 we take outside of the integration, because this 2 sin omega t to cos omega t, we can write it directly as 0 to t sin 2 omega t dt. And then we know, for sine and cos, the integration over a complete cycle is always 0. So that implies P average, which is written as 10 by T 0 to T sin 2 omega t dt, it will be 0, because this will lead to 0. So the average power dissipated over a cycle will be 0. So the correct option is option D. I hope this is clear to everyone. Now we will move to question number 2. Question number 2 says the peak value of an alternating current is 10 amperes. Then RMS value of current will be, options are option A 5 ampere, option B 5 root 2 ampere, option C 5 by root 2 ampere, and option D 0 ampere. So I'll give you a few minutes and then we will discuss. So if we discuss, so what is peak value? So peak value is basically the maximum value or the amplitude. The maximum value, or we call the amplitude of the signal. Basically amplitude is the maximum value of the signal. So in general we write Vt is equals to V peak sin omega t, because the maximum value of sin omega t is 1. So the maximum value of Vt is V peak. However, what is RMS value? Basically RMS value is called the effective value of a varying quantity. So what is RMS value? So it is a measure of the effective value of a varying quantity. Effective value of a varying quantity. Basically, it is the equivalent DC value that you deliver the same power to a resistor as that of the AC signal. So, the VRMS is equals to, which is the equivalent DC value that will deliver the same power to a resistor. So, VRMS is given by 1 by T root over integration 0 to T Vt mod square dt. Basically, it is the average value. So, if you calculate in general for sinusoidal waves, so for sine waves, the integration over 1 by t 0 to t, that comes out 1 by 2. So, if you do that, it will be 1 by root 2 factor will come into the calculation. So, V RMS is equals to V peak divided by root 2, which is 0.707 volt. Similarly, for IRMS, it is written as I peak divided by root 2, which is, so I'm extremely sorry for the background noises because these are really unavoidable and I can't get out of it. So this is 0.707 I. So similarly, if you come to our question, in the question it is given the peak value is 10 ampere. So RMS value will be I peak divided by root 2. So 5 by root 2, which is so this is the answer. So which is 5 by root 2. So the correct option is option C. I hope this is clear to everyone. Now we will move to question number 3. Question number 3 says, in an AC circuit, the instantaneous value of EMF and current are E equals to 20 sin omega t and current is 4 sin omega t minus pi by 3 amps. The average power consumed in watt is, options are option A 80 watt, option B 40 watt, option C 20 watt, and option D 10 watt. So here the instantaneous value of EMF and current is given. So the EMF is given by 20 sin omega t and current is 4 sin omega t minus pi by 3. So these are the value of current and voltage that are given, and we need to find out the average power. So I'll give you a few minutes and then we will discuss. So here if you see the question here, the instantaneous value of EMF and current is given and we need to find out the average power. So here we don't need to use that formula over where we were averaging over a complete cycle. So here what we will do, so there is a formula for average power which is Im Em by 2 into cos phi. So what is Im? So where E is being represented as Em sin omega t and I is written as Im sin omega t plus phi. So here phi is the phase difference, Em and Im are the peak value. So Em is the peak value of E and Im is the peak value of I. So or we can write P average equals to E RMS I RMS cos phi, because E RMS is equals to 1 by root 2 EM and I RMS is equals to IM by root 2. So here if we calculate, so from the question here, so here you see it is sin omega t, it is omega t minus pi by 3. So for our question, phi is pi by 3. So what will be the value of average power? So average power will be E RMS into I RMS into cos phi. So E RMS is 20 by root 2 into I RMS is 4 by root 2 into cos 60 degree, because E is given as 20 sin omega t, I is given as 4 sin omega t minus pi by 3. So if we calculate it, it will be 80 by 2 into cos 60 is 1 by 2. So 40 into 1 by 2, which is 20 watt. So the correct answer is option C, 20 watt. I hope this is clear to everyone. Now we will move to question number 4. Question number 4 says a resonant AC circuit contains a capacitor of capacitance 10 to the power minus 5 farad and inductor of inductance 10 to the power minus 3 Henry. The frequency of resonance is, options are option A 10 to the power 4 radian per second, option B 100 radian per second, option C 10 to the power minus 8 radians per second, and option D 10 to the power minus 4 radians per second. So these are the 4 options. I'll give you a few minutes to solve this question, and then we will discuss what will be the correct answer. So here a AC circuit is given which has a capacitor as well as an inductor. So capacitor and inductor. Capacitor has capacitance 10 to the power minus 5 farad, and inductor has inductance 10 to the power minus 3 Henry. Now for resonance, we know for capacitance it is Xc, which is 1 by omega c. For inductance it is XL, that the impedance, which is omega L. So for resonance, Xc equal to XL, that implies 1 by omega c equals to omega L, that implies omega square equals to 1 by LC, or that implies we get omega is equal to 1 by root over of LC, which is the resonance frequency. So in our question, what will be the resonance frequency? So omega resonance will be 1 by root over of LC radian per second, because it is omega, it will be radian per second. So 1 by 10 to the power minus 5 into 10 to the power minus 3 root over divided by 1. So it will be 10 to the power minus 8, or it will be 10 to the power 4 radian per second. So the correct answer is option A, 10 to the power 4 radians per second. Now this is question number 5. Question number 5 says an alternating current source of frequency 50 Hz is joined to a combination of resistance, a capacitance, and an inductor in series. The potential difference across the inductor, the resistance, and the capacitor are 13, 4, and 10 volts respectively. The electromotive force of alternating current source in volt is option A 27 volt, option B 7 volt, option C 5 volt, and option D 19 volt. So here it is says an alternating current of frequency 50 Hz. So the frequency of the AC current is 50 Hz, and it is connected to a combination of resistance, capacitance, and inductor. All are in series. So it is a series RLC circuit, and the potential difference across the inductor, the resistor, and the capacitor are 13 volt, 4 volt, and 10 volt respectively. So across each there will be potential drop. So VR, VL, and VC. So those values are given, and we need to find out the electromotive force of alternating current. And these are the options. So I will give a few minutes to solve this question. But before we solve this question, we will first discuss the concepts of series RLC circuit, and then we will solve this problem. So I will give you a few minutes to try this, and then we will discuss. So let's first discuss a few concepts related to the series LHC circuit, and then we will solve the problem. So, as the name implies, so series LHC circuit means resistance, inductor and capacitor all are in series. So this is the supply voltage Vs, this is resistor, inductor and capacitor. The voltage drop across resistor is VR, voltage drop across inductor is VL, voltage drop across capacitor is Vc, and the current is given by I is equals to Im sine omega t. Now, uh, if we talk about the impedance, so the impedance of resistor ZR is given as R, which we can write as R 0 degree. So both voltage and current are in phase. For inductor, it is ZL, which is J omega L. That implies it is omega L plus 90 degree. That is the voltage leads the current by 90 degree. So voltage leads the current. Similarly, for capacitor, it is 1 by j omega c, which is 1 by omega c minus 90 degree, where current leads the voltage. And if you talk about the uh, waveforms, so suppose this is 0, this is positive and this is negative. Suppose this is uh, the starting point. Suppose this is the voltage VR. So this will be VR, and for VL it leads by 90 degrees, so it will be like this. So it is VL, and for capacitor it lags by 90 degree, so it will be this is BC. Where what is B or what is I? So I is of the form. So for resistance, voltage and current are in phase. For inductor, voltage leads by 90 degree. For capacitor, current leads by 90 degree. And now if you talk about the phase diagram, so what will be the phase diagram? So for individual, so here both current and voltage are in phase. So this is I, this is VR. This is I, this is VL for inductor. This is I, this is VC, which is for capacitor. and if you uh, make the sum of all, so what will be the phasor diagram? It will be like, suppose this is axis, so this is BR, this is VL, this is VC, and this is I. This is 90 degree, this is 90 degree, and this is the the way the time moves or time varies. So this is 0, this is T by 4, this is T by 2, and this is 30 by, sorry, this is 30 by 4, and this is T, 30 by 4. So what will be the value of Vs? So this will be the impedance, sorry, EMF Vs. So Vs will be VR square plus VL minus VC square, or Vs is root over of VR square plus VL minus VC square. So now let's, or we can say the total impedance Z, we can write as R square plus omega L minus 1 by omega C square root over at the angle. So cos phi will be R by Z, sin phi will be XL minus XC by Z, and tan phi will be XL minus XC by R. So now let's solve the problem. So let me move the slides to so now coming to the problem, the electromotive force of the alternating current source that we need to find out. So we just calculated what is the value of EMF. So the value of EMF V square is given by VL square minus VC square, sorry, VL so the EMF is given by V square equals to VL minus VC plus VC square plus VR square. That implies V equals to 13 minus 10 square plus 4 square root over. Because here it is mentioned in the question, VR is 4 volt, VL is 13 volt, VC is 10 volt. That implies what will be V? V is 13 minus 10, so 3 square 9 square plus 4 square, sorry, 3 square plus 4 square root over, which is 16 plus 9 root over 25 root over, that is 5 volt. So the correct answer is 5 volt, which is option C. I hope this is clear to everyone. Now we move to question number 6. Question number 6 says a 10 ohm resistor and a 0.02 Henry inductor are connected in series to an AC source operating at 20 volts and 500 radian per second. The phase angle between the current and the voltage source voltage is option A 30 degree, option B 45 degree, option C 60 degree, and option D 80 degree. So here it is a series RL circuit. So this is 10 ohm, this is 0.02 Henry, and the source is operating at voltage. So this is 20 volt and 500 radian per second, and we need to find out the phase between current and voltage of the source voltage. So I'll give you a few minutes to try this question, and then we will discuss what will be the correct answer. So like in uh, series LCR circuit, for series LR circuit, the impedance is given as Z equals to R square plus XL square root over. That implies R square plus omega L square root over. So tan phi becomes XL by R. That implies phi equal to tan inverse XL by R. So what will be the value of tan phi? So from the question, tan phi is omega L by R. Omega is given as 500 into L is 0.2 Henry divided by R is 0.02 Henry, and R is 10 ohm. That implies it is 10 divided by 10, which is 1. That implies phi is tan inverse 1, tan inverse tan pi by 4, which is 45 degree. Phi is 45 degree, so the correct option will be option B. Now we move to question number 7. Question number 7 says the resonant frequency of a LCR circuit is nu. If the capacitance is made 4 times but inductance remains the same as that of the initial, then the new resonance frequency will be. Options are option A 4 mu, option B 2 mu, option C mu by 2, and option D mu by 4. So these are the 4 options. I'll give you a few minutes to try this question and then we will discuss. So, so as we have already discussed one problem related to this resonance frequency, so we know at resonance XL equal to XC, that implies omega L equal to 1 by omega C, so which comes out to be omega is equals to 1 by root over of LC. That implies nu 0 is 1 by 2 pi root over of LC. So the new resonance frequency will be nu prime equals to 1 by 2 pi root over of L into 4C. 1 minute. So the new resonance frequency will be, so here so in the question it is mentioned the capacitance is made 4 times but the inductance remains the same. So capacitance is 4C and inductance is L, so it will be 1 by 2 pi into 1 by 2 LC, so it will be 1 by 2 into 1 by 2 pi root over of LC. So this is nu 0 by 2. So the new resonance frequency will be nu by 2 or nu 0 by 2. So option C is the correct option. Now we move to question number 8. Question number 8 says, which of the following relation is significant for metals when the temperature increases? So options are option A, resistivity increases and conductivity decreases. Option B, resistivity decreases and conductivity decreases. Option C, resistivity decreases and conductivity do not, resistivity and conductivity do not change with temperature. Option D, none of the above is true. So here the question is related to the metals. So we know metals are generally good conductors of heat as well as electricity because they have charge carriers and heat carriers. Basically, the metal have many enough free electrons, and those free electrons they are available for carrying heat energy as well as the current. However, now if the temperature changes, how the things change for a metal. So since there are plenty of electrons, so if the temperature increases, the collisions between the electron that increase. So due to that, the resistance, because we know resistance is only due to the collisions between the charge carriers, so the resistance or the resistivity that increases, and as a result the conductivity decreases, because since the electrons can't travel much distance due to collisions, so the conductivity will obviously decrease. So if you talk about the property of metal, for metals the charge carriers are free electrons and they are plenty. So when, so you can consider a scenario, suppose there is a room and in that room there are 10 people and we will instruct them to go outside of the room through a door. But if in that room we feel 100 people and then we tell them to go outside this room, so when they will try to move, they will collide with each other and that's why their motion will be affected. So that will lead to the resistivity. So with increase in temperature, the resistivity increases and the conductivity, that is sigma, that decreases. So the correct option is option A. And also that's why we called as, for example, uh, uh, there is a quantity which is called as alpha, basically which is called as the coefficient of resistivity or temperature coefficient of resistivity, that basically establish a relation between the resistance of a material at temperature T and the resistance of that material at temperature 0 or any reference temperatures. So that is given by RT equals to R0 1 plus alpha T, where alpha is given by RT minus R0 by R0 into T. So when alpha is positive, that is RT is greater than R0, and we call it as positive coefficient of resistance, and when alpha is negative, that means RT is less than R0. So the example of alpha positive is, for example, RT minus R0, so alpha positive will be, uh, the example will be metals and it will be semiconductors, because for semiconductors a very few electrons are available to uh, carry the current. So when we increase the temperature, the extra energy that is utilized to free more electrons, so the more charge carriers are available at higher temperatures, that's why the resistance decreases. So here alpha will be negative and here alpha will be positive. So this is like, this is the way they behave. So with increasing temperature, the resistivity of metal increases, but the resistivity of semiconductor decreases. Now we move to question number 9. Question number 9 says a wire has a resistance of 5 ohm at 0 degree Celsius and 20 ohm at 200 degree Celsius. Find the temperature coefficient of the resistance of the material of wire. So here you see, since with increasing temperature the resistance is increasing, all values are positive. So alpha are positive here because the temperature, with increasing temperature resistance increases. So these are four options: 0.016 per degree centigrade, 0.015, 0.005 and D 0.025. So these are the four options. I'll give you a few minutes to think to solve this question and try to solve, because we have already discussed the formula, and then we will discuss. So let's discuss. So like we have already discussed the formula for resistance at a temperature T is given by RT equals to R0 1 plus alpha T. So that implies alpha equals to RT minus R0 divided by R0 into T. So here RT is 20, T is 200 degree centigrade, R0 is 0, T is 0 degree centigrade. So this T is delta T, which is 200 degree So alpha is 20 minus 5 divided by 5 into 250. So it is 1 by 3 into 1 by 250. So sorry, 3 by 250. So alpha equals to RT minus R0 divided by R0 into T, that implies 20 minus 5 divided by 5 into 200, because T is 200 minus 0, it is 200 degree centigrade. 15 by 5 into 1 by 200, so 15 into 10 to the power minus 3, that is 0.015 per degree centigrade. So the correct option is option B, 0.015 per degree centigrade. Now question number 10. So question number 10 says find the temperature at which the resistance of a metal wire would be double of its resistance at 0 degree centigrade, given alpha is the temperature coefficient resistance for metal, which is 5 into 10 to the power minus 3 per degree centigrade. So this question is again pretty much similar to the previous question, but here we need to find out the temperature value, not the value of alpha. So here we need to find out the temperature at which the resistance of the metal wire will be doubled of its resistance at 0 degree. Suppose at T it is R or 2R. So at T equal to 0 it is R. So in that case, what will be the value of alpha? So alpha is RT minus R0 by R0 into T. That implies P is RT minus R0 by R0 into alpha. So what is T? So T is RT is 2R0 minus R0 divided by R0 into alpha. So it is R0 by R0 into alpha, so it is 1 by alpha. That implies 1 by 5 into 10 to the power minus 3, which is 10 to the So 1000 by 5, that is 200 degree centigrade. So the correct answer is option A, 200 degree centigrade. So when if the coefficient of resistance is 5 to 10 to the minus 3 per degree centigrade, so there will be the resistance of the wire will be doubled when the temperature changes from 0 to 200 degree centigrade. I hope this is clear to everyone. With this, we come to the end of today's interaction session. In the next interaction session, we will be solving a few problems that will be based on week 11 course contents. So today we solved a few problems that was based on the concept of series LR circuit, series RLC circuit, as well as how the resistance of the metals and other materials vary with temperature. Depending upon that, we can calculate the value of the resistance at certain temperature, or we can calculate the required temperature for which we need a desired value of the resistance. So in the next week, we will discuss problems that will be based on the concepts of RC circuits. So the nature of RC circuit is somewhat different as from RL circuit. So we will discuss that in the next week. So that's it from my side for today. So in the next session, we will discuss more about the course contents. Thank you.